All right, let's dive into one of the most famously mind-bending ideas in all of physics, Albert Einstein's special theory of relativity. Seriously, this is an idea that didn't just tweak our understanding of the universe, it completely rewrote the rules of reality itself.
And you know what? Let's just get this out of the way right now. If this whole topic makes your brain feel a little twisted, you're not alone. You are in very good company. That quote, that's from a physics professor at MIT. He actually tells his students that he had to study it 4 different times before he felt like he really truly got it. So our goal here isn't to make you an expert overnight, but to give you a real taste of this incredible world-changing idea. So let's start with a big question that's probably on your mind. I mean, why should we even bother wrestling with something this tricky? Well, because the payoff is huge. This isn't just about some obscure cosmic phenomenon. It actually reveals a hidden, deep connection between forces we experience every single day. And here it is, the big reveal. Special relativity shows us that magnetism, the force that makes compasses work and motors spin, isn't really a separate force at all. It's just what the electric force looks like when it's moving relative to you. They are 2 sides of the exact same coin. And this theory, this is the key that unlocks that mind-blowing connection. And here's the really wild part. All the bizarre consequences of special relativity, and trust me, they get bizarre. We're talking shrinking rulers, slowing clocks, the works. All of it is built on just 2 beautifully simple, unbreakable rules. And these are the rules of the game. First, the laws of physics are the same for everyone. So things like gravity or how a ball bounces, they work the exact same way no matter how you're moving as long as you're not speeding up or slowing down. And second, the speed of light in a vacuum is the ultimate constant. It is the cosmic speed limit. It doesn't matter if you're standing still or rocketing through space. If you measure the speed of a beam of light, you will get the exact same number every single time.
Now, when we say for everyone, what we really mean is anyone in what physicists call an inertial frame of reference. It sounds super technical, but it's really just a point of view that isn't accelerating. So picture someone standing on a train station platform, and then picture someone else on a train that's gliding past at a perfectly steady speed. Both of those are inertial frames. Okay, so we've got our 2 rules. Laws of physics are the same, and the speed of light is the same. Now let's see what happens when we really take these rules seriously. This is where things start to get weird and wonderful. So the first shocking consequence is that time isn't absolute. It's flexible. If you're watching a clock move past you, you will actually see it ticking more slowly than your own clock. And this isn't some trick of the clock's machinery. It's a fundamental property of time itself.
We can actually visualize this with a little thought experiment, a light clock. So imagine on our moving train, there's a device that shoots a pulse of light from the ceiling straight down to a sensor on the floor. For a passenger on that train, the light just travels a short, simple, straight-down path. But for the person on the station platform watching this train zip by, they see the light pulse travel a longer, diagonal path because the train is moving forward while the light is in the air. And here is the absolute key. Remember rule number 2? The speed of light must be the same for both people. But the person on the station clearly saw the light travel a longer distance. So, if speed equals distance divided by time, and we know the speed has to stay the same, but the distance got longer, well, something's got to give, and that something is time. For the math to work, the time interval itself has to stretch out. Time must pass more slowly for the moving clock.
But it's not just time that's relative. It turns out space is too. Just like moving clocks are measured to run slow, moving objects are measured to be shorter, shrunk in their direction of motion. This is called length contraction, and it's basically the other side of the time dilation coin. For the laws of physics to be consistent for everyone, that's our first rule, remember? Space has to be just as flexible as time. So if time stretches for a moving object, space has to contract to keep everything in balance. Okay, I know what you're probably thinking. This all sounds like a really bizarre philosophical game, right? Slowing clocks, shrinking rulers. Does any of this stuff actually happen in the real world? The answer is a huge, resounding yes. And the proof is literally raining down on our heads from the sky every second. Which brings us to one of the most elegant proofs in all of physics, the paradox of the cosmic ray muon. This tiny little particle is all the evidence we need that these relativistic effects aren't just theory, they are a core part of how our universe operates. So here's the puzzle. Way up in our atmosphere, about 20 kilometers up, cosmic rays from space are constantly creating these unstable particles called muons. Now, muons have a ridiculously short lifespan, just 2 millionths of a second. Even traveling at almost the speed of light, simple math says they should only make it about 600 meters before they decay into other particles. But we detect them all the time, right here on the surface of the Earth. How is that possible? Relativity solves this beautiful paradox from two different points of view. From our perspective here on Earth, we see the muon moving incredibly fast, so its internal clock slows way down. Time dilation stretches its lifespan, giving it just enough extra time to survive the 20-kilometer trip. But now let's flip it. From the muon's point of view, its lifespan is totally normal. Instead, as it looks ahead, the entire 20 kilometers of atmosphere shrinks down, length contraction, making the journey short enough for it to complete before it decays. So get this, we have two completely different explanations. One says time stretched, the other says space shrank, but they both lead to the exact same observable result. The muon makes it to the ground. This is our first rule in action, right here. The laws of physics are perfectly consistent, no matter your point of view. Now, this deep connection between space and time leads us to another really famous consequence of relativity. It turns out our universe has an ultimate speed limit, and it is a law that simply cannot be broken. Normally, if you're on a train moving at 100 kilometers per hour and you throw a ball at 20, someone on the ground just adds them up. They see the ball moving at 120. Easy. But that common sense addition totally breaks down near the speed of light. If you're on a rocket moving at 95% the speed of light, and you run down the corridor at 95% the speed of light, you don't reach 1.9 times the speed of light. The special formula of relativity gives you 0.9987 times the speed of light. A little bit faster, but still under that cosmic limit. And this isn't just a mathematical trick. It's because as you approach the speed of light, it takes more and more and more energy to go just a little bit faster. You can get incredibly close, but you can never actually reach it. It's the universe's final red line. So all of this, the slowing clocks, the shrinking rulers, the cosmic speed limit, it all points to one really profound conclusion. Time and space are not the separate, rigid backdrops we thought they were. They're flexible, and they're tangled up with each other. What one person measures as pure time, another person, moving differently, measures as a mixture of both time and space. They are woven together into a single four-dimensional fabric we call spacetime. And really, that's the thought I want to leave you with. We started this journey by finding out that magnetism is just electricity in motion. We ended by seeing that time itself is tangled up with space. It proves that some of the most fundamental things we assume about our reality are not fixed at all. They depend entirely on our point of view. And that really makes you wonder, what else is just a matter of perspective?